All right. Did everybody read the shooting competition application? What you were supposed to get from that is there is a point on the target that you want to hit. And I said call it L because L is what we're going to use for the limit when we go back to the definition of the limit. So let's say L is where you want to hit, and there is a certain amount of offness. That's okay. I mean, the bullseye is not just one tiny pixel. It's has a certain radius, and anywhere in that radius is okay. To hit anywhere inside that radius, then you've got to hold your gun pretty steady. The target, the bullseye, is 3 feet from the ground. So if you could hold your rifle precisely 3 feet from the ground without moving, then if your rifle is, well, I can't think of the word in it, not tuned in, that's trumpets, not rifles, but if it's
Accurate.
sighted in, yes. My husband's a deer hunter, I'm supposed to know that word. If your rifle is sighted in perfectly and you hold it exactly 3 feet from the ground without shaking at all, you'll hit the bullseye, hit right smack in the middle of the bullseye. But it's hard to hold a rifle that steady, and so probably it's going to be shaking just a tiny bit. The amount of shaking of the gun will determine where that bullet hits the target. And what in my made up scenario, let's see, I said, if you want the bullet to be within epsilon units, of the L, then the amount of shaking is going to have to be within delta units of 3 feet. And the closer you have to be to L, then the steadier you're going to have to hold your gun to exactly 3 feet. And the other thing that I wanted you to get from this is absolute value is distance, right? So when I say absolute value of x minus 3, that's the distance from where your gun actually is to where it's supposed to be at exactly 3 feet level. Absolute value of x minus 3 is the distance between perfectly level and where your gun actually is pointed at the time you pull the trigger. Absolute value of P minus L is the distance between where your bullet hits and that dead on target. All right, so if you've read this, let's go back and compare it to the definition of limit. Let f be a function defined on an open interval. What does an open interval mean? Well, it doesn't have to include the endpoints. It's an interval, but not necessarily including the endpoints. Let f be a function defined on an open interval containing some x value of c, then except for possibly at c. We said a hole in the graph doesn't affect the limit. So there could be a hole in the graph at c, but other than that, f has to be defined on some open interval containing c. And let L be a real number. When you say the limit as x approaches c of the function is L, that means for any epsilon greater than 0, with our target practice here, epsilon was the distance that P had to be within the limit. The distance between P and the limit had to be less than epsilon. And if for every epsilon greater than 0, there exists a delta greater than 0. Delta was the distance that your rifle was actually from the perfectly level 3 feet. For any epsilon greater than 0, there exists a delta greater than 0, such that, just read this, the distance between x and c. C is some constant on your x-axis, and the distance between x and c is less than delta and greater than 0. If that distance is greater than 0 and less than delta, then the function value, f of x, the distance between the y value and L will be less than epsilon. You tell me how close you want f of x to be to the limit L, and I can find a tiny enough delta such that if the distance between x and c is less than delta, then the distance between y and L will be less than epsilon. Now, that's a lot to soak in. Let's look at this picture. F of x, y equals f of x is this function. That function consists of all the y values you get from plugging x's into f. C is some constant on the x-axis, and delta is the distance to the left of C or to the right of C that some x value is. X is some value within delta units of C. If you tell me that the limit of this function as x approaches C is some number L, what that means is you give me some tiny distance for epsilon. Epsilon might be 0.01 or 0.001 or 0.0001. You tell me how close you want the function value to be to L, and I'll tell you how close x has to be to C in order to achieve that. Now, nodding, that makes sense? I'm so impressed, because it didn't make sense to me for maybe years. I'm faking ignorance here. Didn't make sense to me for a while. If absolute value of x minus c is the distance between x and c, and f of x minus L is the distance between some function value and L, then for any epsilon, any tiny distance you give me, there's some corresponding delta such that if the distance between x and c is less than that delta, if the wiggling of the gun is less than delta units, then my bullet will hit within epsilon inches of L. The smaller epsilon you choose, the smaller delta I'm going to have to choose. The closer your bullet has to be to the bullseye, the less wiggling my gun can do. That makes sense? You give me a tiny, tiny epsilon, I got to be really, really close to the bullseye. I'm going to have to let my gun wiggle less. I'm going to have to choose smaller delta. I'm going to have to choose. As a matter of fact, I can get f of x infinitely close to L by letting x get infinitely close to C. That is what is meant by this notation, limit of f of x as x approaches C is some L. Now, maybe that makes a little bit of sense to you, but hold on. I think we can make it make more sense. Your homework tonight is delta epsilon proofs. And I want them to make sense to you, not just be copied. All right, because delta depends on epsilon. How much wiggling your gun can do depends on how close you have to hit the target, bullseye. How close you get to C depends on how close you want f of x to be to L. The first step in doing one of these proofs is choosing your delta as some expression involving epsilon. Your delta is always going to depend on epsilon, which, comparing to the application I gave you, the amount your gun can wiggle always depends on how close your bullet has to be to the bullseye. To do this, you start with this absolute value of f of x minus L, the distance between y and L. You start with that is less than epsilon, and you work on this expression until it becomes this expression. That'll make sense when you see the example. Once you have chosen the appropriate delta, you actually do the proof. Step one is not your proof. Step two is writing the definition in terms of the function you're given and the x value you're approaching. Step two is find an appropriate delta. And then step three is show that if absolute value of x minus c is less than delta, then absolute value of f of x minus L will be less than epsilon. It's actually just step three that's your proof. All right, so first proof I typed out for you. I typed all of it for you so you could just listen. I know it's hard to to listen and write at the same time. So just listen to this one. Prove that the limit as x approaches -3 of 2x plus 5 equals, and in the homework, you actually have to find the limit and then prove it is what you said it is. Well, what kind of function is this? Y equals 2x plus 5. That's a linear function. And you can actually plug -3 into that function and you'd get -1. So if you imagine graphing the line y equals 2x plus 5, actually I did right here. When x approaches -3, sure enough, it looks like y is not only close to, but exactly is -1. All right, first thing you're going to have to do to be able to do these proofs in tonight's homework is know the definition. So first few times, I'm just going to copy it. Show that for, let's see, here's what you're trying to prove. So show that for every epsilon greater than 0, there is a delta greater than 0, such that if the absolute value of x minus c, well, c is the number that x is approaching. So in this example, -3 is your c. X minus -3 is the same as x plus 3. I guess I could have put that in as a middle step, but that's why there's a plus here. It's x minus -3. If the absolute value of x plus 3 is between 0 and delta, then the absolute value of f of x minus L, that L is the limit you found, is less than epsilon. On the test, if this is a 5-point problem, then that's probably 2 points for knowing your definition and stating what it is that you're trying to prove. Step 2 is find the delta. Find out how much your rifle barrel can wiggle in order to be as close to the bullseye as the judge says you have to be. Well, we start with, I like this for you. You start with this expression and work on it until it becomes that expression. So we start with the absolute value of f of x. In the place of f of x, I put 2x plus 5. Absolute value of f of x minus -1. Or I just typed +1 because that's what minus -1 is. Absolute value of 2x plus 5 minus -1 or +1 is less than epsilon. That's always what you start with. And you work on it until what you hope to come up with on the left-hand side is absolute value of x minus c. In this problem, it's going to be absolute value of x plus 3. So if this is less than epsilon, let's see how much we can clean up the left-hand side. That'd be the absolute value of 2x plus 6. I could factor a 2 out of that. And if 2 times absolute value of x plus 3 is less than epsilon, then x plus 3 would have to be less than epsilon over 2. And so the delta, the amount my rifle barrel can wiggle, is going to have to be half as much as my bullet can be from the bullseye. Because the slope of the line is 2. Slope of the line is 2. So however close I want to be to my bullet hitting the bullseye, my barrel can only wiggle half that much. So far, so good. Riley, is this making a little bit of sense so far?
Only a little bit.
It's the notation. It's easy to get bogged down. Your eyeballs aren't used to seeing epsilons and deltas. So every time I see delta, I'm thinking that's how close my rifle barrel has to be within exactly 3 feet. And every time I see the epsilon, I think that's how close my bullet is to the perfect center bullseye. All right. Now, after you finish step 2, after you've chosen your appropriate delta, step 3 is pretty much just copying this down backwards. Step 3 is your actual proof. And anytime you do a proof, you have to start with the hypothesis, the thing that you're trying to prove. So look back at your statement 1. You're saying for every epsilon greater than 0, there exists a delta greater than 0, such that if begins your hypothesis. And what you're trying to show is if that hypothesis is true, then your last line has to be, then the conclusion is true. So how do we get from the hypothesis to the conclusion? Basically, it's this backwards. If absolute value of x plus 3 is between 0 and delta, then I can put the delta I've chosen. I can put this in place of delta, and then multiply both sides by 2, where here I divided by 2. Distribute that 2, where here I factored out the 2, and then split that 6 back into 5 minus -1, or 5 plus 1, so that this is exactly what you were trying to prove. This is your f of x minus L will be less than epsilon. All right. Let's look at that geometrically. We've looked at it in a shooting competition. We're going to look at it geometrically, and then for homework, you're going to read an application about if in business, for your profit to be within however many dollars you want of your ideal profit, your sales are going to have to be pretty close to your sales target. That makes sense? All right, so what we've discovered is for the function f of x equals 2x plus 5 to be within epsilon units of -1, we have to choose an x that's within half that distance of -3. If we want f of x to be between -1.5 and -0.5, that's a half a unit from -1. If we want our y to be within a half a unit of -1, then our x is going to have to be within a quarter unit of -3. So this is actually my L right here. That's bullseye. That's what I'm wanting to hit. But if I want my y's to be within a half a unit of -1, then my x is going to have to be within a quarter of a unit of -3. And you can see that on the graph for any epsilon greater than 0. It doesn't have to be a half. I could say I want my y to be within 1/100th of -1. Then my x would have to be 1/50th a unit from -3. All right, it's not exploded yet. Let's do 2 more, and then maybe we can get started on 2.3. The problems in the homework, like I said, first you have to find the limit. And I made these easy in that all 3 of the examples I did, the function f of x is linear. If f of x was uglier, if it was quadratic or cubic or transcendental, heaven forbid, this would be much harder. So we're only going to do the linear ones to get you some idea of what the limit definition means. All right, so first thing we have to do is find the limit of the function 3x minus 2 if x equals 2. How do you find that? Yeah, since that's a linear function, you can just let x be 2 and see what y actually is. If x is 2, then y would be 4. 3x minus 2 is my f of x. Which one of those is my c? C is what x is getting close to, and that 4 is my what? That's my L. In your homework tonight, I have to see step 1, 2, and 3, pretty much identical to what I typed on the previous page. So the first thing we're going to have to do is know this definition. Step 1, show that for any epsilon greater than 0. You tell me how close you want my bullet to be to the bullseye. That's what epsilon is. For any epsilon greater than 0, there exists a delta greater than 0. It doesn't make sense to talk about negative distances. For any epsilon greater than 0, there is a delta greater than 0 such that if, I have to look back at the definition, but that hypothesis is if the absolute value of x minus c is between 0 and delta. For this problem, that would be absolute value of x minus 2 is between 0 and delta. Then the distance between f of x, what do we put in place of f of x? 3x minus 2 minus L will be less than epsilon. Here's my C, here's my f of x, and here's my L. L is the bullseye that I'm trying to hit. Epsilon is some tiny distance that it's okay to be for my bullet to be from 4, and delta is how close my x has to be to 2. So that's 2 points. Step 2, you start with your conclusion, absolute value of, let me put that 3x minus 2 in parentheses so you can see it better. Absolute value of 3x minus 2 minus 4 is less than epsilon. And we want to work on that left-hand side until it just becomes what? the absolute value of x minus 2. So we could combine like terms. We could factor out a 3. And we could divide both sides by 3. And say, however close my bullet has to be to hitting 4, my x is going to have to be within a third of that distance of 2. So choose delta to be a third of any epsilon anybody gives you. And step 3 is your actual proof. You start with your hypothesis. You start if the absolute value of x minus 2 is less than delta, and then you can substitute in what you've decided to let delta be. Delta is epsilon over 3. So let epsilon over 3 in the place of delta, and basically work that backwards. Now, on the previous page, on my first example that I typed for you, I kind of dropped the left-hand side. Technically, I shouldn't have. I did, but I'm going to keep up with it here like a good math person. You multiply all 3 sides by 3, you have 0 is less than 3 times the absolute value of x minus 2 is less than epsilon. And if you distribute that 3, you have 3x, absolute value of 3x minus 6 has to be between 0 and epsilon. And you might have to look back up here at what you want your conclusion to be. This is what you want your conclusion to be. So all you have to do is split that 6. And again, so again, absolute value of 3 times x minus 2 minus 4 will be less than epsilon. And then you put your most famous exclamatory statement. Mine is voila. Yes, sir. It would not. I was thinking up here, I put the parentheses around the 3x minus 2. That's what I meant to do. I'm so glad you said that. Yeah, that would make a big difference. You know, I like to make a mistake at the end. How I finish things. If you want the limit to be within a quarter of a unit of 4, then how close is the x going to have to be to 2? Epsilon's a quarter of a unit, then delta is going to have to be a third of that. What's a third of a quarter? A 12th. X is going to have to be within a 12th of a unit of 2 in order for y to be within a quarter unit of 4. And that's because the slope of the line is 3. All right, let's do one more. And then, yes, I think we will get to make up a little lost time. Start 2.3. Number 3, prove that the limit as x approaches 4 of the function 4 minus x over 2 is blank, what goes in the blank? Since that's a linear function, you can just let x be 4, and 4 divided by 2 is 2, 4 minus 2 is 2. So here's my function. Here's my c that x is getting close to, and here's my L that y is getting close to. Step 1, state what it is that you're trying to prove. And it has to be a full sentence with capitalization and punctuation. Show that. For any epsilon greater than 0, no matter how tiny. You don't have to write the no matter how tiny. There exists a delta greater than 0. Such that that first line is going to be the same on every proof you do, but you have to write what it is you're trying to prove before you start proving. Show that for any epsilon greater than 0, there exists a delta greater than 0, such that if absolute value of x minus c, what are we putting in for c? All right, the distance between x and 4 is less than delta, then the distance between f of x and 2 will be less than epsilon. Here's my c, here's my f of x, here's my L. What are we trying to do in step 2? What's the goal of step 2? It's to find an appropriate delta. So to find an appropriate delta, we start with what we want to end up with and find its relation to x minus 4. Start with absolute value of 4 minus x over 2 minus 2 is less than epsilon. What do you think we would need to do in order to boil that down to just absolute value of x minus 4? Combine like terms. Absolute value of 2 minus x over 2 has to be less than epsilon. And then what? I don't know. I'm not trying to clear out the fractions here. The next step in our previous 2 examples was factor. You could factor out a 1/2. You know, that's the slope of that line. So factor out a 1/2. And what would that leave you inside the absolute value? 4 minus x. You're not sure? All you have to do is distribute that 1/2. And sure enough, it gets 2 minus x over 2. And then what? Dividing by 1/2 is the same as multiplying by 2. So multiply both sides by 2, and you'd have absolute value of 4 minus x is less than twice epsilon. In terms of the shooting competition, that would be, you tell me how close my bullet has to be to dead on center, and I can let my rifle shake twice that much. It doesn't sound very realistic in terms of a shooting competition, but just that's what it would be in this one. So we're going to choose our delta to be twice any epsilon you give me. And step 3, what do you start with? You start with your hypothesis, because now you're actually doing the proof. You say if 0 is less than absolute value of x minus 4 is less than delta. If that is true, then I'm hoping I can prove that this is true. What would I do first? I'm sorry, what? There's, you know what? We can do that. I don't think I would say let delta be -2 epsilon. I don't think we'll do it there, but here we may have to do some multiplying by negative. We'll see in just a minute. All right. Oh, I know the answer to that, Lily. Took me just a minute, but because the absolute value is there, x minus 4 is the same as 4 minus x. Without the absolute value, that's not a true statement, but with the absolute value, that is true. All right, so start with this. Put our 2 epsilons in place of delta. And then what? Divide all 3 sides by 2. And then what? I wouldn't know what to do next if I didn't have this step 2 written down. But basically, I'm just going backwards. I'm saying if this is true, I didn't divide the middle by 2. There. It looks just like this. And like I said, because of the absolute value, it doesn't matter if you have 4 minus x or x minus 4. Now distribute that 1/2. And then split that -2 back into the conclusion you want. It's the same as x over 2. And 4 minus 2 is the same as that 2 inside the absolute value. And my second favorite exclamation, I'm trying to remember what one of the funny students said. I can't remember what she used to write, but it cracked me up. The actual proper thing to write at the end of a proof is QED, but I don't remember the Latin words it stands for. QED, the Latin translates to, and it is proven. I like the one. All right. Does that make more sense than yesterday at the very end of the class when I just read that definition and scared me? Okay. Tonight, you're going to read a second application, like I said, about revenue and profit. I thought it was sales and profit, but it's revenue and profit. to make sure that it makes sense to you, make sure that this bottom line makes sense to you. And then you have to do, how many problems on day 2? Right here. You have 4 proofs, 41, 47, 48, 49, that have to look identical, step 1, step 2, step 3, to the 3 examples we did. Now, you went on the test, just like this. Make sure you know your definition of a limit. All right, let's see how far we can get in 2.3. Finding limits analytically. What are the 2 ways we found limits yesterday? We graphed them and put our fingers on the graph and moved it in closer to some C value that X was approaching. And then we looked at the graph to see what Y was getting close to as X got close to C. That was one way. What was the other way we found the limit? By making an XY table and picking X's that are getting close to C and seeing what Y gets close to. That's fine, but a little time consuming. And I think what you saw from the couple of examples that we did today, if you have a linear function, you can just plug the value of C into the function to find the limit. As a matter of fact, as long as there's not a hole in the graph or a vertical asymptote or that crazy fluctuation going on, you can find limits by direct substitution. That's what we're going to call just plugging in the X and getting the Y. So let's look at these 3 examples, and then we'll talk more about direct substitution. If you have the limit as X approaches C of some constant, your function you're talking about there is just f of X equals a constant. What does f of X equals a constant look like? Or Y equals a constant look like when you graph it? It's a horizontal line, and the limit of that function, all the Y's are B. Whatever B is, all of the Y's are that. So if I just say the limit as X approaches anything of 3, all the Y values are 3, no matter what X is approaching. Second one, that function that we're talking about is f of X equals X. If you graph f of X equals X, it's just this line that bisects the first and third quadrants. So if you want to know what Y is approaching as X approaches -4, it's just -4 because Y is the same thing as X. That's what that equation's saying. Y and X are the same thing. So whatever X is approaching, Y is going to be approaching the same thing. And number 3, if you have limit of X to a power as X approaches C, it's just going to be C to the power. If we look at the squaring function, and the squaring function is a parabola, if I want to know the Y value of that parabola as X approaches 2, I can just put 2 into the squaring function and get a 4. Let me show you these theorems on page 83, 84, and 85. 2.1 is what I typed for you. 2.2, the first one, let me get my little flashlight going here, my spotlight. The first one says, if you have the limit as X approaches C of a constant times a function, just find the limit of the function, L, and multiply it by the constant, B. Number 2 says you can take limits term by term. Step 3 says the limit of a product is just the product of each limit. You can take limits of factors by just multiplying the two limits. Same thing for quotients. The limit as x approaches c of a quotient is just a quotient of the limits. All of these are really just saying you can use direct substitution as long as what you're substituting doesn't make the expression undefined. That's all it's saying. What else? 2, 3. If p is a polynomial function, this first part's just saying you can use direct substitution to find the limit as x approaches c of some polynomial p of x. Just plug c into the polynomial. And this one is saying if r is a rational function, then as x approaches c, you can just plug c into the numerator, plug c in the denominator, but you have this, hey, watch out for as long as c, at q of c, doesn't give you 0. And we'll have to talk about what to do when it does, but you can't use direct substitution to find the limit of a rational function as the denominator's getting close to 0. Uh, 2.5, limit of a composite function. Again, it's just telling you all the things you can use direct substitution on. And last one, 2.6, you can use direct substitution on the limits of transcendental functions. The first 6 are trigonometric functions, 7's the exponential function, 8 is the natural log function. You can use direct substitution to find all of those as long as whatever you're substituting doesn't make the function undefined. So the first whole bunch of these, 6 through 36, I may add those on to the homework to give me more to grade, but 6 through 36 are all problems that you can do by direct substitution. I don't even think there's any point in writing down any of those examples. I'll just say on number 18, as the limit as x approaches 3 of this function, if you put 3 in place of x, you'd have square root of 9. That numerator is just 3. The denominator would be 5. So that limit is 3/5. All right. Same thing. What do 19 through 22 say? Yeah, I think I skipped those in the homework. I asked you to do 5 through 17 and then skip to 23 through 35. 23 through 35 are transcendental functions. Number 24, the limit of tangent x as x gets close to pi. Can you evaluate that by direct substitution? Can you evaluate tangent pi? Pi radians, the negative x-axis, what's the ordered pair? -1, 0. So what's tangent of pi radians? 0. If that had been tangent pi over 2, then I would have to say undefined or does not exist, because I know that tangent has vertical asymptotes. It's undefined over 5 half pi's. How we do? We're doing good. Through 35. All those are direct substitution, and then skip to 47. So I know where I want to stop in the homework. I want to do this one example, number 60, and then we'll call it a day. I'll tell you when we see how far we get right here. I think I know, but hang on just a jiffy and I'll tell you exactly what I will take up tomorrow because I want to see your proofs. All right. Theorem 2.7 is functions that agree in all but one point. I should have shown you that before I went away from the book. Theorem 2.7 says if the function f of x will reduce to the function g of x, maybe f of x is a rational function and you can factor and cancel in such a way that g of x is the simplified version of f of x. So there's going to be a hole in the graph coming from that factor that you canceled out. But we know holes in the graph don't affect the limit. We can still just plug c into our simplified function. Can't plug c into f, then simplify f and plug c into g. So I think that's what happens on number 60, and that's where we'll stop. And all that crazy notation that wouldn't have made sense 3 weeks ago. You may need to look at the examples in the book. Yay, do if you need to. But number 60 says the limit as delta x goes to 0. Have you ever seen the slope formula written as delta y over delta x? Delta y is the difference in two y values. Delta x is the difference in two x values. So delta x is a distance between x2 value or two x values. And this limit is saying as that distance gets closer and closer to 0. In other words, as the two x's get closer and closer to each other. Here's the function, and it is crazy. Can I evaluate it by direct substitution? Can I just put 0 in for delta x? That would be 0 in the denominator. So when you can't use direct substitution, that's called indeterminate form. And there are 3 tools for resolving indeterminate form, fixing indeterminate form. And the only one we have to talk about is the reducing the rational expression. So let's see if we can simplify that to something we could use direct substitution on. And very important, don't lose your limit notation in any step. If you just start working on simplifying that rational expression and lose your limit function, you may not remember to put it back on there. That numerator, I'm going to FOIL out x plus delta x. It'd be nice if I didn't have to write it down twice and take 3 steps to multiply it out. I'm good at squaring the binomial now. I just know it's the first term squared plus twice the product of the 2 terms. And when I write delta x, I'm going to put it in parentheses so I can see it's one thing. It's not 2x triangle x. It's 2x times delta x. And then delta x squared. And then minus your x squared and over your delta x. And then I see some of that numerator gives me 0. The x squared minus x squared is 0. Just to keep myself from having to write down 2 more steps, I'm just going to say, what can I do to the numerator now that I've canceled those x squares? What can I do to the numerator in order to be able to simplify that further? You can factor out delta x. Don't lose your limit notation. Factor a delta x out of that numerator, and what will be left inside that numerator? 2x plus delta x. Cancel those delta x's now that you've factored them out. And then tell me this limit, if my delta x, if my distance between 2 x's was getting so tiny that it was almost just one right on top of the other. If delta x was getting to be so close to 0 it disappeared, what would be left of that limit? 2x. And you don't know it, but you just found the derivative of the function y equals x squared. know that. Right now, you just, that's the difference quotient. This is the difference quotient with using a delta X instead of an H. You've simplified the difference quotient. Now you're taking the limit of the difference quotient. And then in chapter 3, you're going to find out the limit of the difference quotient is the definition of the derivatives. The biggest thing in calculus. All right, so homework, I'm going to say, I'll just put it right here. Page at the bottom of 2.3 notes, page whatever 2.2 is, dang it. It drives me nuts if I don't have page numbers. 79, page 79. The 4 problems you're supposed to do proofs for are 41, 47, 48, and 49. And then in 2.3, you can do up to 35 for sure. I think you could do 47, 48, and 51. 47, 49, and 50. There. Here's your homework for tonight, and I will take all of that up tomorrow. Nope, just what I put in brackets right there. Up to 35 is direct substitution, and then I think 47, 49, 51 are just simplify the rational expression and then use direct substitution. Mr. Riley, did that raise your temperature again?
I don't know if I feel so well.
Hey, did you watch the video for 2.1?
I did.
Okay, so you're used to seeing limit something something and finding it by either making a table or making a graph.
Somewhat.
Okay, you can get better at it. Well, now we're not making a table or looking at the graph, but
Right.
just using direct substitution
Okay.
so far. And then tomorrow we'll talk more about what about when you can't use direct substitution.
Okay.
All right, email me if you have any questions. I'll put this video on YouTube.
All right. Thank you.
See ya. Hey, you want to
See ya.
Zoom tomorrow?
Yeah, I'll Zoom tomorrow. Thank you.
All right, see ya.
See you.